Can you turn this way?
Probably not. Find where it is.
It's the top. Okay.
Okay.
Try now.
Hello, can you hear me?
Oh, great.
Okay, great.
Okay. Are you ready for me to introduce you?
1 second, let me clip this to my jeans pocket so that I don't. Okay.
So like the
Yeah.
a little after 11, but you can always look at us for time.
Sounds good.
Okay. So hey everyone, welcome to like the last stretch of talks of the conference. Woo! That's because it's exciting to have more talks. So I'd like to introduce Reila Zheng. She's here from the University of Toronto, and she's going to tell us about Sharkovsky ordering on the Mandelbrot set. Ooh.
Thank you, Noelle. All right, so let's get started. So first I'm going to introduce the setup. And let me just ask, does anyone have trouble seeing what I wrote on the board? If you do, please put your hand up. Okay, good. So the setup is we're going to deal with the simplest family of rational maps on the Riemann sphere. So z goes to z squared plus c. C is some complex number, and this is a map from from the complex plane to the complex plane. And for this map, the critical point is going to be 0, and the critical value is c. So you can iterate a map like this for a fixed c, and you can analyze the dynamical behavior. And the first thing that you can notice is that the critical point is either going to escape under iteration to infinity, or it's going to stay bounded. So we're going to characterize the set of parameters for which c as a parameter has the property that under iteration, the critical point is bounded. So this is what's called the Mandelbrot set. And a cartoon of this is what I've drawn on the left. So this set, you have these kind of open regions where dynamically the behavior is stable under perturbation. One thing maybe I will say, the question that I'm going to ask today has to do with one ordering of these hyperbolic components. So we say a vane on the Mandelbrot set is an embedded arc from some tip to the main cardioid. And the main cardioid is exactly this component that I labeled 1. In the middle, looks kind of like a cardioid. So the question that I'm going to ask, maybe before I do that, let me just give an example of a vane. For instance, if you go from the leftmost tip all the way back down, this is an example of a vane. Another example of a vane is if you do this. Pretend I drew this completely within the Mandelbrot set. Maybe some other example. You could have a vane that bifurcates off like this. So the question that I'm going to ask is, you have associated to each of these hyperbolic components, within this hyperbolic component, the period of the critical orbit. So the question that I'm going to ask is, for a vane V, let Cn comma V be the hyperbolic component of period n closest to the main cardioid along V. What can we say about the ordering of these CNVs along the vane? Maybe let me just note that this is hyperbolic component of period n closest to the main cardioid if it exists. So if you remember Sarah's talk on the first day of this conference, there are several parameters with period 5 on the real vein. And C5 will be the component of period 5 closest to the main cardioid. Any questions about the setup? Okay, so let me introduce the other half of the title of this talk. And this is the classical Sharkovsky ordering. So the classical theorem of Sharkovsky, maybe let me give the ordering first. So this is an ordering, a total ordering on the natural numbers, given by 3 is bigger than 5 is bigger than 7 and 9 and so forth, all the odd ones. And all of these are bigger than 2 times the odd ones. Bigger than 2 to the n times the odd ones. And after a countable family of these, you're eventually going to have in decreasing order 2 to the n, 2 to the n minus 1, all the way down to 2 and 1. So this is an ordering on the natural numbers, and it describes the following behavior for maps on an interval. So the theorem of Sharkovsky says if f is a continuous map on an interval, the set of periods of f, I'm going to denote it as per f, is a tail of this ordering. And a tail, I just mean everything that comes after some number, and it doesn't necessarily have to have an initial element, and vice versa. So every tail of this ordering, there exists a continuous map on the interval such that the set of periods of that map are exactly is exactly given by this ordering, the tail of this ordering. Any questions about this? Is this okay? Okay. So maybe let me say also as a remark, as a consequence to Sharkovsky's theorem, if we have a map f on the interval such that the set of periods is exactly given by all the elements that are less than, let's say, an odd number, and n is not 1, then all orbits of period n, where n is that odd number, are what are called Stefan cycles. And what these things are is if you imagine your interval map, your Stefan cycle is going to start from the middle, and it'll map on one side, and then the other, and then the other, and then the other, and so forth. It's going to alternate back and forth before eventually coming back to the middle. Any questions about this? Okay, so this fact is going to come in handy later on, but let me give the other ingredients of complex dynamics. So if you were here for Sarah Cook's talk on Friday, she describes that for these kinds of, like for a parameter within the same stable region, you have this cartoon that sort of describes the dynamical behavior. And that's the first tool that we're going to use, these dynamical cartoons. And this is a thing that Hubbard came up with, which is essentially you have these kinds of maps So given any parameter in a hyperbolic component, its dynamical behavior, all the interesting aspects of its dynamical behavior is described by a tree, where that tree, the vertices are given by the orbit of the critical point, and the edges are just like this way of connecting between them. And it has the property that your map f sub c, when restricted to this tree, it's a continuous map on this tree. So for any c in a hyperbolic component, let's say capital C, the critical orbit Fn of 0, this set, form the vertices of this tree, and the edges between them map homeomorphically to paths under the map f sub c. So f sub c restricts to a map on this tree, t sub c, and this is a continuous map on a tree. To give an example, so on Friday, Sarah Cook talked about some parameters such as the rabbit, where in the dynamical plane of the rabbit, you have a Phil-Julia set that looks something like this. And there are these fractally copies of these kinds of like three-pronged behavior. And if your periodic orbit starts from here, maps to here, then maps to here. So maybe let me use numbers. So 0 maps to 1, maps to 2. And these are just points. And the tree that is preserved will be this tree given by just connecting these vertices with edges. And F under iteration, F restricted to this tree is another dynamical system on the tree. Any questions about this? So that's the first ingredient. The second ingredient and this is orbit forcing. And I will attribute this to Milner. And basically associated to each of these hyperbolic components is the sort of dynamical description. So there is a combinatorial description of the critical orbit such that for all the parameters further down from this component, they will have periodic point with that same orbit portrait, and nothing else will contain that orbit portrait. Moreover, every single periodic orbit on a Hubbard tree, somewhere corresponding to some parameter somewhere, has a sort of root of that periodic orbit. So some sort of hyperbolic component whose critical orbit has that orbit portrait. And let me try to say this. So associated to each hyperbolic component is a periodic orbit such that for all parameters C so further down, and I'm going to say it as within a wake at C, at component F sub C has a point, has that periodic orbit. Moreover, every periodic orbit anywhere is associated to such a hyperbolic component. And then the other fact that I will mention is that these wakes, so these regions for which you have this dynamical behavior, the regions are either nested or disjoint. So to give an example, if I consider the component that's labeled 2, so this is what's called the basilica for complex dynamicists, this region in green corresponds to all the parameters that will have a periodic orbit somewhere with that dynamical behavior of this periodic orbit with period 2. Nothing else will. You can do the same thing for this component, the airplane, as Sarah mentioned. So everything within this wake of the airplane contains a periodic orbit with the behavior of the airplane, but nothing else. Any questions about this? Okay, so that's the second ingredient. And let me give the third ingredient in complex dynamics. Third thing is the surgery of limbs. So let me maybe describe what happens. For instance, if I had a parameter on the real plane, on the real vein, and I look at that parameter in the dynamical plane. So as an example, consider A, the airplane. And let me just say that this point A is some parameter here. So in the dynamical plane, we can draw in this, this tree that describes all the interesting dynamics of A, and that is going to be this line segment with the critical point 0. 0 maps to some point C here, and it maps to this F's applied twice of the point 0, and that maps back to 0, and the edges between map homeomorphically. And what I can do is this procedure of noticing on this tree, there is going to be a fixed point, which I label alpha. And if I cut the dynamical plane along the rays that land, so if I cut the dynamical plane at this fixed point, I'm going to get 2 sectors, the sector that contains the critical point and the sector that doesn't. And the procedure is I'm going to duplicate the sector that doesn't contain the critical point. And you can duplicate the sector any number of times to get the following. So if I duplicate the sector, what I'm going to get is, let's say if I duplicate it twice, so here is my point alpha, here is my point 0. 0 maps to C1. C1 maps to this point C2. C2 maps to this point F2 of 0, and it maps back to alpha. Basically what I'm doing is I'm taking that sector to the left, and I'm just duplicating the dynamical behavior of it. So this is a procedure that's known as quasi-conformal surgery. And if you do this in the dynamical plane, it turns out that you will end up with another parameter in the parameter space. So instead of this parameter A, we're going to end up with this, let's say, phi of A, where phi is this surgery. And moreover, it turns out that if you do this to the real vein, if you do the surgery, you're going to end up with another arc in the parameter space, and that arc is going to be called a principal vein. So phi of the real vein is going to be a principal vein. The thing is, you can do this in a number of different ways. You can sort of swap the way that you order these sectors in the plane. You can also duplicate the sector instead of duplicating once. You can duplicate it any number of times. And you'll expect to get a vein that, for instance, looks like this, or another vein that looks like this, et cetera, et cetera. Any questions about this? So I've given you all the big ideas from complex dynamics. And let's put some of these ideas together to see if we can say something about the question that I posed earlier, which is what is the ordering of these components of period n along a vein? So the simplest possible case is going to be the real vein. So let me call this section 4, the real vein. And for parameters on the real vein, 0 is real, C is real. So the iterates of 0 are all going to be real numbers. So if you try to connect it via line segments, the line segments are going to form a line segment. So as a remark, if V is the real vein, then C in V will have its Hubbard tree as a line segment. Now, we know from Sarah's talk on Friday that there is a component, the airplane, where the critical orbit is period 3. Hence, the Hubbard tree for the airplane is going to be an interval that has a point at period 3. So by the usual Sharkovsky's theorem, there is a point at period n for every natural number n. By the fact that all the orbits, by orbit forcing, all the periodic orbits are witnessed by hyperbolic components, and the wakes corresponding to the hyperbolic components are either nested or all the periodic orbits of the airplane, the wakes corresponding to them have nested, and so they have to occur somewhere on the real line. And now I'm not going to spell out all the details, but if you're bored, maybe as an exercise, you can think about how this implies that all the components Cn of V exist, and the ordering of Cn of V on the vein V is exactly the Sharkovsky. You can just check that if n is greater than m in this ordering, then that means the component Cn has to contain a point of period m. So therefore, the wake of period m has to be further down. So there must exist a component of period m further down. Hence, Cm has to be closer to the main cardioid. Any questions about this? Is this okay so far? Okay. So I'm not done because it turns out you can say something else. So the thing that I mentioned before about the surgery of limbs, if you remember the fact that when you have, if you're looking at the component Cn along the real vein V, where n is an odd number, under the surgery, if you had, so Cn of V, the critical orbit had to have been a Stefan cycle. Under this transformation, the critical orbit in this map phi of that parameter is going to be a spiral graph. What I mean by that is your critical point is going to spiral out evenly on all the limbs as much as possible outwards before finally returning. So this is going to be useful for determining the ordering on the principal veins. So maybe let me say it like this. So analogous to the Sharkovsky ordering on the real line, there is going to be a partial ordering that describes periodic orbits of a continuous map on a tree. So let me state it like this. If F is a continuous map on an n-branched star, maybe let me say a k-branched star, then the set of periodic orbits, the set of, sorry, of F is a union of tails of I Sharkovsky orderings I up until K. And maybe, just to relate it to the original ordering, I'm going to denote the usual Sharkovsky ordering as the 2 Sharkovsky ordering. Let me give an example of these I Sharkovsky orderings. So for the 3 Sharkovsky ordering, this is going to be a partial ordering on the natural numbers. In the bottom, you're going to have the numbers that are 3 times the usual Sharkovsky ordering. So you're going to have 3 times 3 bigger than 3 times 5 bigger than 3 times 7, etc., all the way down to 3 times 2, 3 times 1, and then after that, you're going to have the number 1. And above these, you're going to have 2 branches, one of the form 1 mod 3, and they're going to be in increasing order. So 4 is bigger than 7, is bigger than 10, is bigger than 13, 16, etc. The other one is going to be of the form 2 mod 3. So 5 is bigger than 8, 11, 14, etc. And there are going to be comparisons in between. So 4 you can say is bigger than 11, 7 you can say is bigger than 17, 5 is bigger than 13, and 8 is bigger than 19, and so forth. If I have time, I can give the actual description of this ordering, but in general for the 2 minutes, okay. For the n Sharkovsky ordering, you have a partial ordering where above you have the branches I mod n, and then below you have 0 mod n. And the continuous map on a k-branch star, then set of periods is union of the tails of the I Sharkovsky ordering for I up to k. And in particular, if F is a spiral graph with k branches, and let's say jk plus I, vertices other than the central vertex, then the set of periods is exactly going to be the set of elements that are less than or equal to jk plus I in the k ordering. So this fact is analogous to the fact about the Stefan cycles. And we're going to use this fact to explicitly determine for some of these principal veins what the ordering is. So I claim that if I look at, for instance, this red principal vein, and I ask the same question, what is the ordering of Cn along this vein? This is going to be given by the 3 Sharkovsky ordering, and it's going to be somehow coordinated by the 1 mod 3 branch. Why is that? So under this transformation, if we had Stefan cycles that are of odd period here, you can check that the number of vertices is going to be, after this duplication procedure, of the form 1 mod n. So that means for those components of period 1 mod n, the set of periodic orbits that it contains is everything below this ordering and nothing else. So for instance, for the component of period 4, the set of periods is going to be everything in this ordering that's covered by this green. And likewise, the component of period 7 is going to be everything below 7 in this ordering and nothing above. So if we put this kind of information together, we know that on that vein, that principal vein, we have C4 is further than the 2 in between because they have to fit somewhere, C11, C14, and then it must be C7, and the 2 in between that, and then it has to be C10, et cetera, et cetera. So you can determine, in some situations, the ordering of the principal vein exactly, and in other situations, you can know which branch coordinated. And then let me just state without writing the other result, which is for these secondary veins, you can also determine that. And the nice thing is that this branch is coordinated by 1 mod n. These other branches are going to be coordinated by I mod n for I ranging from 2 to n minus 1. So for instance, these branches, this is going to be 1 mod 4, this is 2 mod 4, this is 3 mod 4. The ordering along those. And I think I'm out of time, so I will stop here.